Hello, my name is Marlou N Perquin, and this is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology about temporal structures in sensorimotor variability. And in this case, when I talk about variability, I mean intra-individual variability. And intra-individual variability is something that we are all very familiar with in our daily lives. Imagine when you're typing a message on your phone, there will be variability in how fast you press each key. And this is common in all the repetitive actions that we perform in daily life. Now, variability is also very prominent in our experimental data. So even if you give your participant the simplest task that you can think of, like pressing a button on a fixed tone, there will still be a lot of variability in their responses. So here you can see an example of one participant over 1,000 trials of button pressing, and you can see that their responses are not a straight line, but they are highly variable over time. And this is a characteristic that is shared by all repeated measures of sensorimotor actions that we measure in labs. Now, of course, when we are collecting data, we typically do this in experimental labs, and these are completely devoid of any external distractions. However, even in these circumstances, the data still shows a lot of variability. And this means that this variability must somehow arise from fluctuations in our own internal system, which is what we call endogenous. Now, one common assumption about variability is that it is independent over time, meaning that the correlation from trial to trial should be zero. In practice, this assumption is hardly ever met. Variability over time shows clear dependency. So if I'm very fast on a particular trial, then I'm probably going to be fast on the next trial as well. And if I'm very slow on a certain trial, then I'm probably going to be slow on the next trial as well. Although variability and its temporal dependency is omnipresent in our behavior, it remains largely unknown why we are so variable. So intuitively, we are quick to relate variability to our own metacognitive states. For example, when we say things like, I was making a mistake because I wasn't paying attention. And empirical evidence comes from studies on mind wandering, in which participants are occasionally interrupted during the task that they are performing, and they are asked to rate their own subjective on-taskness. And these studies find that when people report being off-task, their behavior beforehand was more variable compared to when they report being on task. And one proposal is therefore that on-taskness also fluctuates over time, and that these fluctuations bring about the temporary structure variability. And here you can see some hypothesized data on this. However, the exact mechanistic links here remain unclear. And also, while these correlations between variability and subjective off-taskness have been found consistently, the effect sizes are typically very weak. On the other hand, variability is an intrinsic and necessary property of our entire system. So for example, even at the level of a single neuron, random noise contributes to whether the action potential will be fired or not. So behavioral variability may arise as the combination of many different underlying mechanisms, each which fluctuate at the different time scale. And despite these uncertainties, some recent attempts have been made to examine individual differences in temporal structure. So one study had participants perform a go-no-go task, and they found that participants who were good at the task, that is, participants who made less commission errors, showed less temporal structures than participants who were worse at the task. However, a second study had participants perform a continuous temporal expectation task. And in this task, participants are shown one stimulus on every trial for a fixed duration, but on some trials, the duration is a bit longer. And this is when participants have to press a button. So instead, this study found that people who were worse at the task, which in this case means they were slower at reacting to the target, these people had more structure. So Of course, these tasks are not exactly the same, and different task demands could lead to different patterns, but both tasks do feature very heavy elements of sustained attention and inhibition. And instead, one question that has not been addressed so far is to what extent temporal structures are actually a reliable individual trait. And intra-individual reliability is very important for studying individual differences because you want to make sure that you're actually measuring something stable. So we aim to investigate this question in our current experiment. And secondly, we were also interested in examining these common assumptions about the relationship between temporal structure and task performance and subjective attentional state in more detail. And thirdly, we wanted to examine the relationship between these temporal structures and stable attention and attention deficit related traits. So to study this, I used the metronome task, and in this, people have to press a button on a fixed tone. So the button press is not a response to the tone, but they have to press when the tone happens. So perfect reaction time would be 0 seconds compared to the tone. And then occasionally participants are presented with a thought probe, and they are asked to rate their attentional state on a scale from 1 to 9, with 1 being completely on task and 9 being completely off task. So we tested this on about 80 healthy participants, and 25 of them performed the task twice. And then all participants filled out 3 questionnaires, 1 on ADHD tendencies, 1 on mind wandering, and 1 on impulsivity. Then to quantify these temporal dependencies, I used 4 different measures. And the reason that I used all 4 of these is because the way that temporal dependency should be measured and interpreted remains quite a controversial topic. And therefore we chose to include all of the most commonly used measures. So the first measure is autocorrelation, and this is simply the correlation between trial n and trial n plus 1. So that's the autocorrelation at lag 1. And then the second measure is the power spectra density. And for this measure, you take the entire series and perform a Fourier transform, then a log transform, and then plot this transform series against the log of the inverse trial number. And on this, you calculate a linear slope. So one thing that I should add is that we performed an extra correction. And in this, I randomly shuffled the original reaction time series and then calculated the transformed series again. And then I did this 100 times. And because these series are randomly shuffled, you would expect that the average of the 100 series would look like a completely independent process. But this is not what we found. So therefore, we subtract the mean series of these 100 shuffled iterations from the original power spectrum, and only then calculate the linear slope. So this slope expresses the dependency over the entire series. So while the autocorrelation captures a very short-term process, this analysis aims to capture a long-term process. So the third measure is the determinant fluctuation analysis. And for this measure, you integrate the series and then divide the series into a certain number of boxes. The values within each window are then detrended. And on these detrended values, you calculate the average fluctuation. That is the root mean square error. And the log of these average fluctuation values are then plotted against the logged window size. And on this, you can calculate a linear slope. And again, we corrected the series here by subtracting the mean of 100 randomly shuffled iterations. Now, determinant fluctuation analysis also aims to measure long-term dependency in one slope. But this analysis puts less weight on the shorter timescales compared to power spectral density. So here are some examples of how to interpret these. A completely independent process, so a white noise process, would show no autocorrelation. The power slope would be flat, so a slope of 0. and the detrendant fluctuation slope would be very shallow, which would have a value of 0.5. And instead, processes with very high dependency would show very high autocorrelations that theoretically never go to zero, and very steep slopes. So these are the first three measures. And then for the fourth measure, I used the time series model RFIRMA 111. And with this model, you estimate two short-term parameters, R and MA, and one long-term parameter, D. The benefit of this approach is that it can actually statistically test if the long-term parameter adds anything substantial compared to only using short-term parameters. So now that we have all these measures of temporal dependency, let's see how reliable these are within individuals over time. So whether they actually capture some kind of stable individual trait. So first, I'd like to show you the task measures themselves. So here you can see the correlation between time 1 and time 2, with each dot being a participant. And this is for the objective performance, so how variable people were at pressing the button, and then how precise they were at pressing the button, how off task they reported to be, so this is the mean attention rating for each participant, and how variable their off taskness ratings were. And for all of these measures, we found that they showed very high reliability over time. Now, the reliability of the temporal structure, however, depended on the measure that we were looking at. So autocorrelation at lag 1 and power spectral density slope showed very good reliability over time, but the RFIRMA parameters did not. So for our first question, we find that yes, temporal structures are reliable within individuals over time, but not all measures of it are. So for our next question, we were interested in the individual differences of these temporal structures. So looking at the results, we found clear correlations between temporal structure and performance. But again, these correlations were not found for the RFIRMA parameters. And to give you some examples of individual participants to have a good idea of the interpretation, on average, participants who were very good at the task, so participants who had very low variability, these participants also had low autocorrelations and very shallow slopes. But on the other hand, participants who were very poor at the task, so who were highly variable, they had very high autocorrelations and steep slopes. With between these participants, no differences in the RFIRMA parameters. And then, however, when we look at their subjective off-taskness ratings, we find evidence against correlations. So here you can see the correlations for the attentional rating mean, and people who were who reported to be more off-task did not show more or less temporal structure. And we also find evidence against correlations for the standard deviation of the attentional rating. So higher and more variable subjective ratings did not correlate with temporal structures. And then when we look at the three attention-related and attention deficit-related questionnaires, ADHD tendencies, mind-wandering tendencies, and impulsivity, again, we find evidence against or any correlations with behavioral variability and temporal dependency. And as such, our findings provide clear evidence against the idea that these temporal structures may relate to fluctuations in the attentional or metacognitive states. So to conclude, we find that although measure dependent, temporal structure indeed seems to be a reliable individual trait. And overall, we find pretty good reliability for most measures, and also that similar measures like subjective ratings or performance tend to correlate well to each other, as such kind of forming clusters of one type of measure. However, the correlations between different types of measures are notably absent, even when we intuitively expect them to be. So thank you very much for listening to my talk. and please contact me for any questions you might have. Thank you.